Hi and welcome. I'm trying to learn particle physics. Today the standard model, and after we've done it, we're going to do morning stretching. And if you participate in the morning stretching, that's at your own risk. And this is already part 10 or something. So now there are many questions still to the standard model. And one question is, for example, why is the heaviest quark weighing 70,000 times more than the lightest one? Now inside of these fermions or these atoms or the protons inside of atoms, there are 6 quarks, and the heaviest one is 70,000 times heavier than the weightiest one, than the lightest one. The standard model gives no explanation for this hierarchy problem as a deeper theory, perhaps a ground unified theory that properly unites quantum electrodynamics and quantum chromodynamics might. Let's do the sentence again. The standard model gives no explanation for this hierarchy problem. The standard model just explains, and at one place we're gonna, if we don't find it somewhere, we're gonna write it good down, like the Newtonic laws to the, whatever it goes to. We have it 1, 2, and 3. I have one was, I'm just gonna say it loud of it, is the electromagnetism, and these are photons zipping through the universe and changing the electrons inside of the atoms. The next force was the weak force, which was combined with the electromagnetism force, but then again separated. The electroweak force, this electroweak force holds the atom together, holds the whatever together, and the strong force holds the whole atom together. Whatever. These 3 things don't explain why one of these 6 quarks is heavier than the other ones. And perhaps a ground unified theory that properly unites quantum electrodynamics and quantum chromodynamics can explain this hierarchy problem of heavier and lighter quarks. Okay, the people are searching for a theory, or basically it's a rule, a law, which says that is that. They are searching for that, what they do mean the theory. They're searching for a law, a sentence written down which says that one is heavier because that, or this is because of that, basically. And then there are also questions like how particle physics might account for the nature of cosmological entities such as dark matter and dark energy, subjects on which the standard model is silent, as indeed it is of the nature of gravity. Okay. Then there are questions like how particle physics might account for the nature of cosmological entities such as dark matter and dark energy. Okay, there are natural entities. Cosmological entities. Now there are things in the universe, they are called dark matter and dark energy, and we don't really understand them. And here's now the question brought up, what has the standard model, which describes how the atoms are built up, or inside of the atoms, the quarks and leptons inside of the fermions out of which the atoms consist, how they are built up. The standard model does not explain what it has to do with dark matter and dark energy. And also not to gravity. All these questions mean that just as the idea of indivisible atoms proved to be far from the last word, we are far from convinced whether the particles' forces of the standard model will be. Okay, and these questions, for example, why is one quark 70,000 times heavier than another one? The standard model does not explain what has to do now with dark energy and dark matter, and also not with gravity. And all these questions, just as the idea of the indivisible atom proved to be far from the last word. So it was the idea some people thought, the atom, that is the end. You can't split it further. It makes a bit sense if you have some stuff and you bring it down to the atoms. If you have some iron and you bring it down to the atom, why should it go smaller than atom? But now the standard model says, no, inside of the atoms there are these protons and electrons and neutrons, and we can split the atom and we can then do things with it. And we're having even more inside of the protons. There are now even 6 quarks and 6 leptons and the Higgs and the W and the Z boson. And a photon. No, I don't know if it's in there. The photons are not in there, but they are transmitting the electromagnetic force from one to the other. But we're going to do it all in detail then later on. Okay, that is actually the end here to the standard model, but that seems to be just an introduction. That means wait here, now spending around 1 minute on trying to understand this graph here, and we'll do the other graph in a minute. The particles of a standard model have been consistently predicted on paper before they turned up in reality. Now there are these 6 quarks, the up, down, strange, charm, bottom, top. The standard model was established around 1974. And I think predicted were the up, down and strange quarks in the 60s, and they were found 10 years later. Also the charm, bottom and top do not understand what the graph means. When was the theoretical proposal? The moon's discovery in cosmic rays in 1936 came as a genuine surprise to theorists, prompting Nobel laureate Isidor Rabi to ask who ordered that. Now they suddenly found moons, and then there was Isidor Rabi, and he said, well, it wasn't on the table, it wasn't planned for today, who ordered it? I don't understand what was predicted invention from. The other one, the standard model, our best understanding of the building blocks of matter and the forces that glue them together. Okay, matter seems to be made up out of fermions, and these fermions consist out of 6 quarks, the up, down, charm, strange, top and bottom quark, and out of 6 leptons, the electron, the muon, the tau, the electron neutrino, the muon neutrino, and the tau neutrino. And then there are the force carriers. The photon transports the electromagnetism from one between these things. But I hate here also between the electrons. Maybe the electrons are these bigger things. Then the electromagnetism force is through the W and the Z boson. And the weak nuclear force through the gluon. And the strong nuclear force through the massive Higgs boson. And I think I read them all wrong, and we have to start the other way around. I don't know. But I think it was photon, electromagnetism, W and Z, weak nuclear, gluon, strong nuclear, mass giver Higgs boson. Now we're through with this little introduction to the standard model. In the next part we will continue with something similar to particle physics. If you're here for particle physics, you can go directly to the next part of particle physics. We will do now the morning stretching. If you participate in the morning stretching, that is at your own risk. We're starting with the shoulder circuits. We're having a good and stable standing legs or feet, and we're going back with the shoulders up and front and down. We're doing forward shoulder circuits. And backwards. And the last side. Now we're breathing in the left shoulder side. And breathe out and fall down. Again, in the shoulders up. And out the shoulders down. Again in. And out and down. Now the upper plug up, breathe in with the arms up. And now reach always with one hand high. Pretend to take an apple hanging high on it. I spoke about it yesterday, I said that. To pretend to take an apple hanging high on an apple branch. Pretend to turn it a bit around and turn it down. And the last 2 times. Now shift up. Arms up to the T, legs wide apart, we're breathing in. And out, we're shifting just with the upper part of the body over to one side. Breathe again in. And out over to the other side. Again in. And another round. Breathe out over to one side over. Again in. Out. And out, we're leaning onto our knees. We're doing the buffalo fighting a sang hour. So breathe in. And out one shoulder at front. Breathe in the shoulder back. And out the other one at front. Okay. Down the shoulder in front. Okay. And out the second time. Shoulder in front, or last time. Okay. And out and we're hanging down. And breathe in. And out we're going over to one leg. Relief getting. And out over to the other leg. Relief getting. Out into the middle. And breathe in. And out and coming slowly round back up and making it top it backwards. Shoulder right. And we're doing the garden pose. The torso pointing to the outside, having an unlimited space between the heels, but we're digging this the arms up. And we're breathing out, sinking down, and we're placing the elbows against the insides of the knees. Now we're feeling straight out back. And out we come into the back up. And breathing in. And out we come again down. Again in, straight up. Out and again up of the back. Breathing in. And out the last time down. We're breathing in, straightening up the back. And out we're coming slowly in one straight line up, the crown of the head first. And now we're doing the seahorse pose. We're having a good standing leg. The other leg is with heel on top of the knee of a standing leg. Do this if you can do it without injuring yourself. Breathing in. And out we're coming down. Thus, according to the theory of quantum electrodynamics, two electrons repel each other thanks to a photon, the boson that transmits the electromagnetic field that appears from nowhere and passes from one electron to another. They are fermions, the particles that make up matter. These consist of 6 quarks arranged in pairs to make 3 generations, identical in all but mass, and 6 leptons, such as electrons and neutrinos, arranged similarly, changing the leg. There are also a handful of bosons, like the photons, that transmit natural fundamental forces between the fermions. 2 electrons repel each other thanks to a photon, the boson that transmits the electromagnetic field. Electromagnetism that is transmitted through the photon. The Higgs was needed to ensure that during the breakdown of the unified electroweak force, the W and Z particles will come up again. Particles acquired mass, confining the weak force to atomic distances, but the photons of electromagnetism didn't allow them to zip across the universe. Now I still don't really get the difference between electron. One of the leptons is called electron. And the photons can repel electrons, but these consist of 6 quarks arranged in pairs, these fermions, identical in all mass, and 6 leptons, such as electrons and neutrinos. Electrons, electron, neutrino, muon, neutrino, tau, neutrino. Baptizing exercise, legs wide apart, breathing in. And out. Let's say up this time. And out, draw the shoulder blades together. Again, in and up. Out and down. Again in. Up. And in. Out. Breathe in, cross the legs. And out. That was the morning stretching. Thank you very much, and until next time.